In the beginning, there was silence. Not the silence of an empty room or a pause between breaths, but a silence so vast it swallowed all possibility of sound, all vibration, all motion. Imagine drifting in that void, where time itself has not yet begun its march, and space is only an unformed potential. Out of this absolute stillness, a question lingers like a faint echo. What waits beyond the silence? This is where the story of the universe truly begins, not with the bang of creation, but with the shiver of anticipation. A whisper moves through the void, too soft to hear, too subtle to define. And yet, it feels as though something unseen is already at work, sketching the outlines of a cosmos yet to exist. It is a haunting image, an empty canvas so wide it cannot be measured, watched over by invisible hands. Before stars ignite and galaxies spiral, before light cuts the fabric of darkness, there is the suggestion of architects, forces or intelligences so immense that their designs lie hidden in plain sight. If creation is a performance, then this silence is the theater before the curtain rises, a stage shrouded in shadow. What kind of beings, what kind of will could orchestrate such a stage? This mystery pulls at the imagination like gravity, urging us to wonder whether the universe was sculpted with intention or whether the silence was simply broken by accident. Picture the first spark of light breaking through the void, a single glimmer that seems impossibly small against the abyss. That glimmer carries with it the power to unravel silence into sound, stillness into motion, nothingness into everything. It is as though the whisper has become a word, and the word has become law. The laws of physics, the laws of nature, the codes by which all things will unfold. Even in its earliest breath, the cosmos feels like a carefully drawn blueprint, a script written long before actors took their place upon the stage. But who or what wrote this script? Was it necessity, cold and mechanical, or was it choice, deliberate and purposeful? This is where the human imagination finds both awe and terror. On one hand, to believe in architects gives us comfort. The universe is not random, but guided. On the other, the possibility that such architects exist suggests that our lives are tiny fragments of a plan we can scarcely comprehend. In the quiet of the void, our minds project stories of gods forging the stars, of titans battling in chaos, of unseen builders crafting the skeleton of existence. Perhaps these are only myths, desperate attempts to explain what lies beyond human understanding. Yet even in the most modern halls of science, the question lingers like a shadow. Is the universe governed by inevitability or designed with care? The silence of the beginning has never truly left us. It resonates in the empty gaps between galaxies, in the dark matter that refuses to be seen, in the uncertainty at the quantum level where existence flickers like a candle flame. We sense the whisper still, a reminder that behind the noise of stars and the rhythm of time, something unspoken remains. The architects, if they exist, have never shown themselves. Their signature, if it exists, is etched into the laws that hold atoms together, the spirals of galaxies, the very heartbeat of reality. And so, we find ourselves asking, is the silence their language? Is absence the clearest mark of presence? This prologue is not an answer, but an invitation. It beckons the audience to step into the vast mystery with eyes wide open, to follow the whisper as it threads through myths, science, philosophy, and wonder. The tone is not one of certainty, but of awe, of reverence for the vast unknown. It suggests that to search for the architects of the universe is not merely to look outward, but also inward, to confront the silence within ourselves. In doing so, we recognize that the story of existence is not a tale told once, but a symphony still unfolding. The whisper from the void is both promise and warning. It promises discovery, the chance to glimpse the hidden blueprints of existence. But it warns of humility, that the architects, if real, operate on scales beyond our imagination, and that what we find may not align with what we hope. As the curtain rises on the grand performance of the cosmos, we are left with a choice. Do we believe the silence hides nothing, or do we dare to believe it hides everything? Long before telescopes peered into the heavens, before equations could describe the orbits of planets and the birth of stars, humanity gazed upward and asked the most haunting question: who built this? In the darkness of early nights, around fires that pushed back the shadows, our ancestors imagined forces greater than themselves. They crafted stories of creators, artisans of the sky, beings whose hands stretched beyond comprehension. These stories were not mere fables. They were attempts to make sense of the incomprehensible, echoes of an ancient longing to find architects behind the universe's grand design. The Egyptians told of Ptah, the divine craftsman who spoke the world into existence, his words shaping the foundations of reality like an architect's chisel against stone. In Mesopotamia, the Babylonians envisioned Marduk battling the primordial chaos dragon Tiamat, slicing her vast body in two to form the heavens above and the earth below. Each myth carries within it the imagery of construction, of shaping raw chaos into ordered form. The cosmos, to ancient minds, was not born but built, not an accident, but a deliberate act of craftsmanship. Across oceans and continents, cultures echoed this theme. The Norse spoke of Ymir, the giant whose body was carved into the elements of the world, his flesh forming the land, his blood the seas, his bones the mountains. In Hindu tradition, Vishvakarman, the celestial architect, designs not only temples but the very structure of the cosmos itself, aligning stars and elements with divine precision. The Greeks imagined Prometheus sculpting mankind from clay, while the gods arranged the heavens as a kind of divine stage set, each star placed with purpose. These stories reveal an astonishing consistency. Across time and geography, humans instinctively reached for builders, architects, craftsmen to explain the immensity of existence. Why builders? Perhaps it is because construction is a human act that bridges imagination and reality. To see a house rise from wood and stone, or a temple carved into rock, is to witness order pulled from chaos. Early humans, awed by the scale of mountains and the brilliance of stars, must have seen in them something akin to colossal monuments, works too vast for mortals, demanding cosmic masons. In their myths, they projected familiar roles, craftsman, potter, warrior, artist, onto the mysteries of the universe. Creation was never random. It was sculpted, just as a potter sculpts clay upon a wheel. These myths, however, were more than explanations. They carried emotional weight, embedding awe, fear, and reverence into the human relationship with the cosmos. A universe built by gods is a universe filled with meaning. The sun rises not just by chance, but because a deity wills it. The stars shimmer not merely as burning gas, but as lanterns lit by celestial beings. Every thunderclap, every eclipse, every storm became a message from the architects, reminders that the builders still lingered, watching, guiding, and sometimes punishing. But within these myths lies a haunting duality. The architects of the ancient world were rarely benevolent alone. They were often violent, capricious, demanding sacrifice, or indifferent to human suffering. Marduk had to slay Tiamat to bring forth order. The Aztec gods required blood to keep the sun moving across the sky. The architects, in these stories, were powerful but not always merciful, reminding humanity that creation was not a gift freely given, but something extracted from conflict, sacrifice, and sometimes cruelty. The awe of being shaped by cosmic builders was always tempered by fear of their unpredictable will. As centuries passed, these myths were layered with new interpretations. Philosophers began to wonder if the builders were symbols rather than literal beings. Plato envisioned a demiurge, a divine craftsman who shaped the material world from perfect forms. The Stoics spoke of a rational logos, a cosmic order embedded in everything, less a god and more an intelligence woven into reality itself. In these shifts, we see the transition from myth to philosophy, from stories to systems of thought. Yet the core remained the same. The universe's architecture, its builders, whether gods, demiurges, or rational forces, lurking behind its order. Even in modern times, echoes of these myths remain. When we speak of the universe as a machine, we invoke the watchmaker, a hidden builder who wound the gears of creation. When we marvel at the elegance of DNA or the structure of galaxies, we feel the same awe that once filled temples and altars. The imagery of architecture has never left us because it reflects our deepest intuition. That order is no accident, that structure implies design, and that beauty often feels like a signature. And yet, there is an unsettling possibility. What if these myths were not mere imagination? What if they were faint distortions of something real, an ancient memory of contact with forces beyond our comprehension, stories passed down and reshaped through millennia? To think of gods as literal architects is unsettling, but to think of them as metaphors for something greater, hidden patterns, unknown intelligences, forces shaping existence from beyond the veil, leaves us with a more profound mystery. The question is not whether the ancients were wrong, but whether their myths concealed truths that science has yet to uncover. The myths of cosmic builders remain with us because they resonate with our hunger for meaning. They remind us that when humanity first looked up at the night sky, we did not see randomness. We saw purpose, design, the work of hands unseen. These echoes continue to ripple through time, weaving into our philosophies, our sciences, even our art. Whether literal or symbolic, they have left an indelible mark on how we think about the cosmos and our place within it. As we move forward, stepping into the lens of science and modern discovery, these ancient stories still whisper beneath the surface. Were they only human inventions born of fear and wonder? Or do they hint at something larger, something architects left for us to remember? The curtain is about to rise on deeper investigations, but the echoes of the ancients remind us that humanity's first instinct was to believe that the universe was not born alone, but built. And the haunting question remains, if there were builders once imagined in myth, what became of them? If myth spoke of gods and titans as the builders of existence, modern science reveals a different kind of architecture, one written not in stone or clay, but in invisible rules. These rules do not shout, they whisper. They are not bound to temples or altars, but they govern every heartbeat of the cosmos. We call them the laws of nature. They are the silent blueprint of everything that exists, the hidden framework on which the universe rests. Like the unseen scaffolding behind a cathedral, they hold the structure of reality in place, ensuring that suns ignite, planets orbit, and atoms bind into the chemistry of life. Without them, there would be no order, no predictability, no possibility for existence as we know it. Gravity is perhaps the most familiar of these laws, yet its strangeness is often overlooked. Imagine the pull of invisible strings binding the planets to the sun, the moon to the earth, and the galaxies together in vast spirals of light. Isaac Newton described it as a force, a constant attraction between masses. Albert Einstein later revealed it as the curvature of space and time itself, as though the universe were a fabric stretched and warped by the presence of matter. Either way, gravity is a sculptor, an architect that shapes galaxies and dictates the dance of stars. Without it, there would be no solar systems, no stable orbits, no worlds capable of nurturing life. Gravity is not a suggestion. It is law, unyielding and omnipresent. Then there is electromagnetism, another pillar of the cosmic blueprint. It is what allows atoms to form, binding electrons to nuclei with unseen threads. It fuels the light of the stars, drives the chemistry of our bodies, and powers the very thoughts sparking across the neurons in our brains. Imagine for a moment a world without electromagnetism, no warmth from the sun, no colors of dawn, no spark of life. This law is both an architect and an artist, painting the universe with light and weaving the complexity of matter into intricate forms. Beyond these lies the quantum realm, where the blueprint becomes stranger still. Here, particles do not act like bricks or beams, but like shadows and whispers. They flicker in and out of existence, appear in multiple places at once, and influence each other across distances that should be impossible. The rules of this domain are unlike anything we experience in daily life, yet they are precise, mathematical, and unbreakable. They dictate the behavior of the smallest pieces of matter, from electrons to quarks, and in doing so, they determine the foundations of the universe itself. To us, the rules appear chaotic, but they are nonetheless strict, inevitable, and profound. Together, these laws form a kind of cosmic constitution. They are not mere guidelines. They are absolutes, observed consistently across billions of years and trillions of miles. Light bends the same way at the edge of a distant galaxy as it does in your living room. Atoms obey the same chemistry in a nebula as they do in your bloodstream. This universality suggests something extraordinary. The blueprint is not local, not limited, but all-encompassing. It governs reality as a whole, as though existence itself is built upon a singular design. But here lies the haunting question: why do these laws exist at all? Why should there be order instead of chaos? The laws could, in principle, be different. Physicists often note that if gravity were slightly weaker, stars might never ignite. If the electromagnetic force were slightly stronger, atoms might not form stable structures. The universe would collapse into nothingness or explode into lifeless dust. The laws are tuned, balanced, poised as if written with careful intention. To some, this is the fingerprint of design, the mark of architects who shaped the rules so that life and beauty could emerge. To others, it is coincidence, one outcome among countless possibilities. Yet the improbability lingers like a shadow over every explanation. Mathematics lies at the heart of this blueprint. Equations are the architect's language, describing the curves of space-time, the vibrations of strings, the decay of particles. Galileo once said that the universe is written in the language of mathematics, and modern science has confirmed his insight again and again. But mathematics itself poses a mystery. Is it an invention of human minds, a clever tool for describing patterns we observe? Or is it something deeper, an eternal structure that existed before humans, before Earth, before even stars were born? If mathematics is discovered rather than invented, then it may be the purest expression of the architect's script, the invisible ink with which the laws of nature were written. The laws of nature do not simply describe, they constrain. They act as boundaries, like the edges of a canvas that limit the painter's brush. Within those boundaries, infinite variety is possible. Stars, planets, oceans, minds, but always within the limits set by the blueprint. This duality of freedom and restriction mirrors the work of an architect. Walls confine a space, but within them, design flourishes. Life itself is an expression of this paradox, thriving not despite the laws, but because of them. Yet there is a silence surrounding the laws themselves. They do not explain their origin. They simply are. Scientists can describe how gravity works, how particles interact, how light moves, but not why these laws exist in the first place. Are they the necessary outcome of logic, unavoidable truths like 2 plus 2 is equal to 4? Or are they choices, deliberate settings in a grand design, adjustable like the dials of a machine? If they are choices, then the architects who set them remain hidden, silent behind the curtain of reality. If they are necessary, then perhaps the architects are the laws themselves, blind and indifferent yet magnificent in their scope. This uncertainty keeps the mystery alive. For every answer the laws provide, they raise a new question. Why does quantum physics allow probability rather than certainty? Why does the speed of light form an absolute limit? Why does entropy, the law of disorder, march relentlessly forward? These are not just technical puzzles. They're clues to a deeper structure, fragments of a blueprint we cannot fully see. To contemplate the laws of nature is to stand before an invisible cathedral, one whose arches and towers stretch beyond sight. We cannot see the architects, but we can trace their work in the perfection of the equations, in the elegance of the constants, in the balance that allows existence to flourish. Whether designed or inevitable, the laws of nature remain the foundation of everything. They're the first blueprint, silent yet unbreakable, whispering to us from the dawn of time. And so, we are left with a paradox. The more we understand the laws, the more they feel like design. Yet the closer we look, the more elusive their origin becomes. It is as if the architects wrote their plan in a language so precise and universal that it could govern creation itself, then vanished into the silence. The blueprint remains perfect and mysterious, leaving us to wonder whether we are observers of a grand inevitability or witnesses to the artistry of unseen builders. Patterns whisper across the universe. They appear in the swirl of galaxies, in the spiral of a seashell, in the branching of a tree, and in the double helix of DNA. It is as though reality itself has been carved with repeating motifs, echoes of a hidden geometry that links the vast and the small. From ancient mystics to modern scientists, humanity has long marveled at these patterns, sensing in them something sacred, a signature written across creation. Geometry is not just mathematics, it is architecture. And when we trace its lines, we find ourselves staring at the possibility of a design too elegant to be accidental. Consider the spiral. From the Milky Way's sweeping arms to the delicate curve of a nautilus shell, the spiral appears again and again in nature. Its form is not arbitrary, but follows the Fibonacci sequence, a mathematical progression that has fascinated thinkers for centuries. The golden ratio, derived from this sequence, manifests in the proportions of leaves, flowers, hurricanes, and even the structures of galaxies. Artists, architects, and philosophers have called this ratio divine, a number that reflects balance, beauty, and perfection. Why should nature, unthinking and chaotic, repeatedly align itself with mathematics that humans recognize as beautiful? Could it be that the spiral is not only a structure of efficiency, but also a symbol, a sign that the blueprint of the cosmos is infused with meaning? Symmetry offers another clue. Snowflakes, with their intricate six-fold balance, grow from nothing more than water molecules aligning under simple physical laws. Yet the result is breathtaking, a frozen geometry that no two flakes share exactly, yet all obey the same underlying rules. On a larger scale, crystals form with astonishing precision, each atom falling into place like bricks in a perfect cathedral. Symmetry suggests order, a sense of balance that transcends chaos. In physics, symmetry governs conservation laws, the idea that energy, momentum, and charge remain constant across the universe. Symmetry, then, is not merely visual elegance. It is a law written into the heart of reality, as if the architects used it as a guiding principle when constructing the cosmos. Fractals extend this sense of pattern into infinity. A coastline viewed from above reveals jagged edges that repeat no matter how closely you zoom in. The same is true for mountain ranges, river networks, and even the branching of blood vessels in our bodies. Benoit Mandelbrot gave these patterns a name: fractals, shapes that echo themselves endlessly at different scales. They are at once chaotic and ordered, unpredictable in detail, yet bound by simple rules. To see a fractal is to see infinity contained in finite form, a kind of cosmic recursion that hints at deeper unity. When lightning forks across the sky or neurons branch in the brain, the resemblance to river deltas and tree roots is uncanny. It is as though reality prefers to repeat itself, to echo its own patterns across different dimensions. The ancients sensed the sacredness of these geometries long before modern science gave them names. In Egypt, the pyramids were aligned with celestial bodies, their proportions reflecting mathematical principles. The Greeks studied Platonic solids, perfect geometric forms that Plato himself believed were the building blocks of the universe. Hindu mandalas and Islamic mosaics echoed the symmetry of stars and crystals, using geometry as a bridge between the earthly and the divine. For these cultures, geometry was not merely abstract. It was a pathway to the truth, a glimpse into the mind of the architects who shaped the world. Modern science, in its precision, has only deepened the mystery. Mathematics describes why spirals emerge in galaxies. They're the result of density waves moving through the stars. It explains why sunflowers arrange seeds in spirals. This optimizes space for growth. It accounts for why fractals appear in trees. They maximize exposure to sunlight and efficiency of resource distribution. Yet behind these explanations lies an unsettling beauty. The rules are efficient, yes, but they are also elegant. Efficiency does not require beauty, yet nature delivers both. It is as though the architects not only built for survival, but for aesthetic wonder, leaving behind a universe that is as pleasing to the eye as it is functional to the mind. But what does beauty mean in the language of physics? Is it merely our human projection, or is it something fundamental, woven into the fabric of reality itself? Physicists often speak of elegant equations, preferring theories that are simple, symmetrical, and beautiful. The search for a theory of everything is not only about completeness, but about elegance, the belief that truth will reveal itself through beauty. This suggests that geometry and symmetry are not accidental byproducts, but fundamental aspects of the blueprint itself. If the universe were truly random, why should it produce such harmony, such balance, such grace? The sacred geometry of the cosmos also raises a darker possibility, that what we perceive as beauty may be a lure, a signal meant to draw us closer to truths we cannot yet grasp. Patterns can comfort us, but they can also deceive. The same spirals that guide galaxies can also mark the path of destruction in hurricanes and whirlpools. Fractals exist not only in the branching of trees, but also in the growth of tumors. Beauty is not always benign. It may be a mask, a way the architects conceal their deeper intentions. Are the patterns signs of benevolence, or warnings encoded in the structure of reality itself? Still, we cannot escape the resonance we feel when we encounter these patterns. There is something almost spiritual in standing beneath a spiral galaxy, or tracing the veins of a leaf, or marveling at the snowflake's perfection. These geometries stir emotions of awe, humility, and connection. They remind us that we are not separate from the cosmos, but made of the same blueprint. Our veins echo rivers. Our neurons echo lightning. Our bodies echo the spirals of galaxies. To study geometry is to realize that we are reflections of a universe, miniature architectures within a grander design. The sacred geometry of the cosmos leaves us with a profound question. Are these patterns inevitable outcomes of physical laws, or are they signatures, deliberate choices inscribed into the fabric of reality by unseen hands? The spirals, the symmetries, the fractals, they're too consistent, too elegant to ignore. They bridge the gap between science and spirituality, between the measurable and the ineffable. Whether accident or intention, they whisper of a universe that is more than matter and motion. They suggest a cosmos that is not only structured but designed, not only functional but beautiful. And so, as we look at the patterns repeating across scales, from galaxies to seashells, from neurons to rivers, we are confronted with the possibility that geometry is the language of the architects. Perhaps it is their way of speaking without words, of leaving a signature that echoes in every corner of creation. The patterns do not tell us who the architects are or why they built, but they remind us of one thing. Design is everywhere, written in lines, spirals, and symmetries. The question is not whether we can see the geometry. The question is whether we have the courage to accept what it implies. Time. We speak of it casually, measure it with clocks, plan our days by it. And yet, when we pause to truly think about it, time becomes the most mysterious force of all. Unlike gravity or electromagnetism, We cannot see or touch time. It has no particles, no visible presence, and yet it governs every aspect of existence with an authority no one can escape. Time is the invisible architect of our lives and the universe itself, sculpting beginnings and endings, growth and decay, creation and destruction. Without time, there is no story, only stillness. But what is time truly? Is it a natural river flowing inevitably forward? Or is it a framework deliberately designed, a stage upon which the drama of existence can unfold? Imagine the cosmos without time, stars suspended in frozen light, galaxies locked forever in still images, every action halted before it begins. Motion itself would vanish. Cause and effect would collapse into meaningless static. The heartbeat of reality would stop. Time is not merely a backdrop to existence. It is the very thread that weaves events together, giving rise to change, to history, to memory. In this sense, time feels less like a neutral feature of the universe and more like a silent architect, laying out the rhythm by which everything must move. We feel its presence most acutely in our own lives. A child grows into an adult, the adult grows old, and eventually, even the strongest body succumbs to the relentless march of time. Empires rise and fall, civilizations flourish and collapse. Forests grow, burn and regrow. Oceans carve cliffs, mountains crumble into dust. Time is patient, but it never stops working. It creates and destroys with equal ease. It gives us seasons to plant and harvest, days to dream and build, and nights to rest and imagine. And yet, it also guarantees our mortality. The same architect that allows us to live ensures that we must die. Time is both gift and curse, a builder and a destroyer. Science seeks to explain time with precision. For Isaac Newton, time was absolute, a cosmic clock ticking uniformly, independent of events. Albert Einstein shattered that certainty, revealing that time bends and stretches depending on speed and gravity. To move faster is to experience time more slowly. To fall into a black hole is to watch time warp into unimaginable distortions. The clock is not universal, it is relative. This discovery transforms time from a simple backdrop into a flexible dimension, a malleable fabric woven into the structure of space itself. Time is not fixed, it can be shaped. And anything that can be shaped begins to look less like inevitability and more like design. Consider the arrow of time, the fact that it seems to move in only one direction, forward. We remember the past, but not the future. We grow older, never younger. Entropy increases, order breaks down, heat dissipates, and the universe drifts toward greater disorder. This arrow defines our perception of reality. But why should time flow forward at all? The fundamental laws of physics work equally well in both directions. They do not care whether events unfold forward or backward. Yet our universe seems to insist on progression, on unfolding events along a singular path. Is this arrow a necessity of thermodynamics? Or is it a deliberate feature of the blueprint, written by architects who wove time to ensure stories could exist, to ensure beginnings and endings would give meaning to the in-between? Philosophers have long debated the true nature of time. Is it real, or is it an illusion created by consciousness? Augustine of Hippo confessed that he knew what time was until someone asked him to explain it. Modern thinkers echo this paradox. Some argue that the past, present, and future all exist simultaneously, like pages in a book, already written, already complete, while our consciousness merely experiences them in sequence. If that is true, then time is not flowing at all. It is fixed, and we are the ones moving, carried along like readers through the chapters of story. In this vision, the architects of time are authors, scripting every moment long before we experience it. Others see time as emergent, not fundamental, arising from deeper laws of physics we do not yet understand. Some theories suggest that at the most basic level, reality is timeless, a static field of possibilities, and that what we call time is simply the way our minds perceive change. If so, then time is a construct, an illusion, but an illusion so perfect that it governs everything we know. An illusion this powerful begs the question, was it engineered, designed with purpose, like scenery built for a play? Yet, for all its mystery, time is also intimate. We measure it not only in seconds and years, but in memories and experiences. The laughter of a child, the grief of loss, the anticipation of love, all are framed by time. Its architecture does not only shape galaxies and stars, it shapes hearts and minds. Time gives depth to our existence. Without it, joy would have no contrast against sorrow, hope would have no tension against despair, and achievement would have no triumph over failure. Time is not just physics, it is meaning. But meaning cuts both ways. Time reminds us of impermanence, of endings we cannot avoid. The same architect that paints sunsets and seasons also tears them away. Civilizations crumble into dust, and even the universe itself may not be eternal. Cosmologists predict possible futures, heat death, where entropy consumes all order and time stretches into meaningless stasis. The Big Crunch, where gravity reverses expansion and time collapses into fire, or endless cycles, where time itself resets, replaying the grand story again and again. In each scenario, the architects of time seem to remind us, nothing built lasts forever. And yet, humanity rebels against this inevitability. We invent calendars to control it, clocks to measure it, histories to preserve it, and myths to transcend it. Religions promise eternity, immortality, or rebirth, ways of escaping the architect's demolition. Science dreams of time travel, of bending the laws to reclaim what has been lost or to glimpse what lies ahead. These dreams speak of defiance, of our refusal to accept time as absolute. If time has architects, perhaps their work is not complete, and perhaps we, too, are apprentices learning to shape it. The deeper we explore, the stranger time becomes. In quantum mechanics, particles seem to ignore the arrow of time, existing in superpositions that do not respect past or future. Experiments suggest that events in the present can influence outcomes in the past, as though causality itself were negotiable. If this is true, then time is not a straight road, but a labyrinth, a structure far more complex than our senses can grasp. It is not a simple river flowing forward, but a web, with pathways that twist, overlap, and loop. Such a structure feels less like accident and more like architecture, deliberate, intricate, enigmatic. Time is the architect we cannot escape, the invisible force that sculpts our beginnings and ends. It builds galaxies and then dissolves them, creates life and then erases it, writes stories and then closes their final pages. It is patient, merciless, beautiful, and terrifying. Whether real or illusory, inevitable or designed, it governs everything we know. And as we stand within its flow, we cannot help but ask, was time woven into the fabric of reality because it had to be, or because someone or something chose it to be this way? The architects of time remain silent, their intentions hidden, but the blueprint they left is undeniable. Every heartbeat, every sunrise, every death, every birth is written upon it. Time is the stage upon which existence plays, and we are both actors and audience. And as the seconds pass, as the years turn, as history unfolds, the most haunting question lingers. If time was designed, who were the architects bold enough to write the laws of beginning and end? Space. At first glance, it feels like emptiness, a vast void stretching endlessly in all directions, a cold, silent backdrop where stars, galaxies, and worlds are suspended. Yet the closer we look, the more this so-called emptiness reveals itself to be anything but empty. Space is structured, layered, and alive with hidden geometries. It bends, curves, stretches, and warps under the influence of matter and energy. It is not a passive stage, but an active participant in the cosmic drama. If time is the rhythm of existence, then space is the canvas upon which that rhythm is painted. And like any canvas, its shape determines the form of the masterpiece. For centuries, humans imagined space as flat and infinite, a limitless arena where objects moved like pieces on a board. Euclid's geometry, lines, angles, and planes dominated our imagination. A straight line was always straight, parallel lines never met, and triangles always added up to 180 degrees. This was space as humans could draw it on parchment, a simple abstraction that seemed to explain the world. But as our vision expanded into the cosmos, cracks began to appear in this picture. Light bent where it should not. Orbits wavered from their predictions. Something was wrong with the board itself. Einstein revealed that the board was never flat at all. His general theory of relativity shattered the illusion of Euclidean certainty, replacing it with a vision of space as a pliable fabric curved by the presence of mass and energy. A planet does not orbit the sun because it is pulled by an invisible force. It falls freely along the curved geometry of space itself, tracing the contours of a cosmic landscape sculpted by gravity. Space is not an empty container. It is the very architecture of reality, bending under weight like a trampoline under a stone. This insight changes everything. Suddenly, geometry is not mere mathematics, it is destiny. The shape of space dictates the motion of galaxies, the birth of stars, and the fate of black holes. Light itself obeys the hidden geometry, curving around massive bodies like rivers following valleys. Even time is not immune. It stretches and slows where space curves most sharply. Space and time are no longer separate. They are fused into space-time, an inseparable whole, a four-dimensional architecture that holds the blueprint of a universe. But what is the true shape of space? Is it flat, curving infinitely outward, or folding back upon itself? Cosmologists have wrestled with this question for decades, using the faint afterglow of the Big Bang, the cosmic microwave background, as their map. The evidence suggests that on the largest scales, space is astonishingly flat, as though stretched taut by forces at the dawn of time. Yet at smaller scales, it ripples and bends, a tapestry of warps created by stars, planets, and dark matter. Space is not uniform. It is textured, dynamic, alive. To grasp the strangeness of this geometry, imagine standing on a cosmic plane so vast that its curvature is imperceptible. Walk far enough, though, and perhaps you would loop back to where you began, as if space itself were a sphere. Or imagine a saddle-shaped universe, open and infinite, curving outward endlessly. These are not mere abstractions. They are real possibilities, each leading to a different destiny for the cosmos. The geometry of space is the script that dictates whether the universe expands forever, collapses into itself, or oscillates in endless cycles. Even emptiness is not truly empty. Quantum physics reveals that space seethes with activity, a froth of virtual particles flickering in and out of existence, a restless ocean of possibility. This quantum foam may define the smallest geometrical scales, where space-time itself dissolves into fluctuations, no longer smooth but turbulent and granular. At such scales, geometry is not continuous but stitched together like the threads of an unseen fabric. If true, then space is not only a canvas, it is a weave with patterns too fine for our eyes to see. For philosophers, this geometry raises haunting questions. If space can bend, warp, and ripple, is it itself fundamental, or is it the manifestation of something deeper? Could space emerge from relationships between particles, or from networks of information, or from a code written at the foundation of reality? If so, the geometry we perceive may be the shadow of a more profound architecture, a hidden order shaping the visible cosmos. And yet, despite its vastness and complexity, space is intimate. It gives us horizons to chase, constellations to navigate, distances to measure. It cradles our planet in its curvature, carries the light of ancient stars to our eyes, and connects us to galaxies millions of light years away. When we look up at the night sky, We are staring into the geometry itself, into the folds and stretches of the cosmic fabric. Space is the silent architect that cradles the universe, a geometry both simple and incomprehensibly complex. Its curves write the laws of motion. Its shape dictates cosmic fate, and its hidden depths may conceal the very code of existence. What appears as emptiness is, in truth, the most intricate architecture of all. But the question remains, was this geometry simply the outcome of blind laws, or was it designed, chosen to allow stars, galaxies, and life itself to exist within its embrace? Mathematics. At first glance, it seems like a human invention. Symbols scratched on clay tablets, numbers etched into stone, equations written on chalkboards by restless minds. Yet, the deeper we look into the universe, the more mathematics reveals itself, not as invention, but as discovery. Its patterns are everywhere, hidden yet undeniable, as if reality itself speaks a secret language, and mathematics is the code. The orbit of planets, the spiral of galaxies, the growth of seashells, the rhythm of waves, the very fabric of space and time, all unfold according to mathematical principles that existed long before humans learned to count. Mathematics is not merely a tool we use to describe reality. It seems to be the blueprint underlying reality itself. Consider the planets. Long before telescopes, ancient civilizations watched their paths across the night sky, puzzled by their wandering motion. To them, the heavens were alive with mystery, gods moving in the firmament. Then came Johannes Kepler, who unlocked the secret. Planets follow precise elliptical orbits, their speeds determined by mathematical ratios. What seemed chaotic became order. What seemed divine became geometric law. Isaac Newton extended this insight, revealing that the force governing an apple's fall was the same force guiding the moon's orbit, a single equation binding heaven and earth. Such elegance feels less like accident and more like a language designed to be understood. But the story does not end with gravity. Look at light. James Clerk Maxwell unified electricity and magnetism into a set of equations so elegant they are often described as poetry in mathematics. From those equations emerged the speed of light, not as a number arbitrarily measured, but as a fundamental constant woven into the equations themselves. It was as if nature whispered her secrets in symbols and ratios, waiting for human minds to listen. Even the strange, probabilistic world of quantum mechanics dances to mathematical rhythms. Equations describe the likelihood of particles existing in multiple states at once, collapsing only when observed. Quantum theory is bizarre, counterintuitive, and defies common sense. Yet the mathematics works flawlessly. Predictions made with quantum equations match experimental results with astonishing precision, down to 10 decimal places. How is it possible that mere human symbols can describe reality so perfectly, even in domains that our senses cannot fathom? This uncanny alignment raises a haunting question. Is mathematics discovered or invented? If we invent it, why does it so perfectly describe galaxies, atoms, and everything in between? If we discover it, where does it exist? Are mathematical truths floating in some eternal realm, waiting to be found, like constellations awaiting recognition? Plato believed they were, envisioning mathematics as an eternal world of forms, pure and unchanging, of which our universe is a reflection. In this sense, the hidden language of mathematics may not be human at all. It may be the language of the architects themselves. Patterns reinforce this view. Consider the Fibonacci sequence, where each number is the sum of the two before it. 1, 1, 2, 3, 5, 8, 13, and so on. This simple progression appears everywhere. In the spiral of galaxies, the arrangement of sunflower seeds, the curl of ocean waves, even the structure of hurricanes. Why does this sequence repeat across such different scales? Is it coincidence, or is it a signature, a recurring phrase in the universal language? Then there is symmetry. From snowflakes to crystal lattices, from the bilateral balance of living creatures to the elegant conservation laws of physics, symmetry emerges as a guiding principle. The laws of physics themselves seem to be born from symmetry. Noether's theorem famously links conserved quantities, like energy and momentum, directly to symmetrical features of nature. In other words, the order we observe exists because the universe insists on balance, on harmony. Mathematics does not just describe this balance, it embodies it. The elegance of mathematics has long been a source of wonder. Eugene Wigner, a Nobel Prize-winning physicist, called it the unreasonable effectiveness of mathematics in the natural sciences. Why should equations devised in the human mind so precisely map the workings of the cosmos? Why should abstract patterns dreamed up on paper later reveal the behavior of particles or the expansion of galaxies? It is as though reality itself is written in equations, and we are slowly learning to read. Yet mathematics is also paradoxical. Within its certainty lie puzzles that defy resolution. Gödel's incompleteness theorems revealed that no mathematical system can be both complete and consistent. There will always be truths that cannot be proven within the system itself. If mathematics is the hidden language of the universe, then even it carries mysteries beyond comprehension, truths that remain forever out of reach. This paradox echoes in our exploration of infinity. The infinite series, the unending decimals, the boundless primes. These are concepts the human mind struggles to grasp, and yet they are indispensable to describing reality. Infinity appears in calculus, in cosmology, in quantum theory, shaping our understanding of the largest and smallest scales. Infinity is the most abstract of all ideas, and yet it governs the concrete structure of existence. What does this suggest about the architects who wove it into the blueprint? Perhaps the most unsettling possibility is that mathematics is not merely descriptive but generative, that the equations do not just map reality but bring it into being. Some physicists argue that the universe itself is a mathematical structure, that what we perceive as particles and forces are simply manifestations of deeper mathematical relations. If true, then the hidden language is not just a way of understanding the cosmos, it is the cosmos. The architects are mathematicians, and their medium is existence itself. Still, for all its precision, mathematics remains cold, indifferent, stripped of the warmth of human experience. And yet, within its coldness lies beauty. A spiral, a curve, a perfect ratio, the golden mean, these stir awe, even emotion. Why should equations evoke beauty? Unless they reflect something fundamental not only about the structure of reality, but about the way consciousness is meant to experience it. Mathematics is the invisible script beneath the visible world, a code that governs the fall of stones and the birth of stars, the flutter of leaves and the pulse of galaxies. It is both abstract and intimate, unreachable and yet ever-present. And as we uncover its secrets, we cannot help but ask, are we deciphering the language of the universe, or are we reading the handwriting of its architects? Symmetry. At its core, it is balance, a mirror image, a reflection that feels both pleasing and inevitable. From childhood, we're drawn to it, faces that appear balanced, patterns that repeat, objects that feel whole because each side echoes the other. But in the universe, symmetry is not merely a matter of aesthetics. It is power, a principle so fundamental that it underlies the very laws of nature. Symmetry is not just beauty. It is order, conservation, and stability. It is the hidden scaffolding that keeps the universe from collapsing into chaos. Imagine a snowflake drifting down from the sky. Each delicate branch mirrors the others, creating a crystalline geometry of perfect harmony. Or consider a butterfly's wings, painted in twin patterns that reflect one another. These are surface examples, glimpses of symmetry's allure. But go deeper, and you find the same principle governing atoms, molecules, forces, and even the birth of the cosmos itself. Symmetry is not coincidence. It is a universal law. physicists discovered that symmetries explain why certain things never change. Energy is conserved because the laws of physics do not care where you are. Shift the entire experiment to another location, and the results remain the same. Momentum is conserved because the laws do not care when the experiment takes place. Yesterday, today, or tomorrow, the equations still hold. Noether's theorem, one of the most profound revelations in science, revealed that every symmetry corresponds to a conservation law. Symmetry is not an ornament of the universe. It is its foundation. Without it, energy could vanish, momentum could dissolve, and the cosmos would unravel. But symmetry is not static. It hides, it breaks, and in breaking, it gives rise to complexity. Consider the universe at its beginning. Physicists believe that the newborn cosmos was perfectly symmetrical, a seething sea of uniform energy. Yet perfect symmetry cannot last. It is unstable, like a pencil balanced on its tip. And so, in the first fractions of a second, symmetry broke. Matter separated from energy, forces split apart, and the diversity of the universe was born. Gravity, electromagnetism, the strong and weak nuclear forces, these pillars of physics emerged because symmetry fractured. From imperfection came creation. This paradox is haunting. Symmetry creates order, but breaking symmetry creates variety. Without symmetry, there is no law. Without broken symmetry, there is no universe rich enough for stars, planets, and life. We live in the balance between symmetry and its shattering, a dance of perfection and imperfection that shapes everything we see. Look again at nature, and you will find this dance everywhere. A seashell spirals outward with near-perfect geometry, yet no two are identical. A human body reflects bilateral symmetry, yet within, the heart tilts left, the liver sits on one side, and the brain itself carries asymmetrical functions. Symmetry gives the framework, but breaking it allows individuality. Beauty is born not only from order, but from the subtle deviations that make each pattern unique. On a cosmic scale, symmetry is woven into the fabric of space-time itself. Einstein's equations describe a universe where the geometry of space respects symmetrical principles, curving in ways that preserve balance. Quantum field theories extend this, showing that particles exist because of underlying symmetries in mathematical fields. The photon, the gluon, the Higgs boson, each is tied to symmetries that dictate their behavior. Remove the symmetry, and the particle vanishes. The universe itself is held together by an invisible lattice of balanced laws. And yet, symmetry conceals mysteries. Physicists once believed the cosmos should be perfectly symmetrical in matter and antimatter. Every particle should have a twin opposite. If that were true, the universe should have annihilated itself into pure light long ago. But it didn't. For reasons still not fully understood, matter gained the slightest advantage, the smallest asymmetry, enough to tip the scales and allow galaxies, stars, and people to exist. This tiny crack in symmetry is the reason we are here. Imperfection, once again, was the midwife of creation. The philosophical implications are staggering. If symmetry is the law of the cosmos, does it hint at a deeper order, a design chosen for stability and harmony? And if the breaking of symmetry is what allows creation, does that mean the architects of the universe deliberately wove imperfection into the blueprint, ensuring that life and diversity could emerge? Perfect order may be sterile, but broken order is fertile. It is in the cracks that existence blooms. We see echoes of this principle in art and music. A melody repeated too perfectly becomes dull, but when variation enters, when symmetry is gently broken, beauty arises. A painting that balances shapes and colors pleases the eye, but its asymmetries give it soul. In the same way, the universe seems to balance symmetry and asymmetry, harmony and dissonance, order and chaos. Its beauty lies not in perfection, but in the tension between perfection and its breaking. Symmetry is the architect's compass, a tool that shapes the laws of physics, guarantees conservation, and provides balance. But asymmetry is the architect's brushstroke, the deliberate deviation that makes the design come alive. Together, they form the hidden dialectic of creation, the dialogue that gave rise to stars, to atoms, to life. And as we peel back the layers of the universe, we are left with a haunting question. Is symmetry simply the natural tendency of order, or is it the chosen signature of intelligence, the mark of a hidden hand that new creation required both perfection and its breaking? Since the dawn of civilization, humans have looked to the skies and sensed harmony. The ancient Greeks, staring at the night canopy scattered with stars, believed that the cosmos was not chaos but order, a grand symphony where celestial bodies moved in rhythm. They called it the music of the spheres, a cosmic melody, inaudible to the ear, yet woven into the architecture of existence. It was not sound in the ordinary sense, but the harmony of proportion, geometry, and motion. The idea was simple yet profound. The universe is not silent. It sings through its patterns. To the philosopher Pythagoras, numbers were not abstractions, they were divine truths. He discovered that musical notes could be expressed as ratios. A string half the length of another produced a sound an octave higher. A string two-thirds as long produced a perfect fifth. Music was mathematics, and mathematics was the language of the universe. If simple ratios could generate beauty in sound, then perhaps the heavens themselves followed the same principles. Planets and stars, moving in their orbits, must also be producing harmony, a hidden symphony only the mind could perceive. This vision enchanted thinkers for centuries. Plato imagined the cosmos as a living being endowed with soul and harmony. Johannes Kepler, one of the great architects of modern astronomy, revived the dream in the 17th century. While struggling to understand the orbits of planets, he looked for patterns not only in geometry, but in music. In his masterwork, Harmonics Mundi, The Harmony of the World, Kepler proposed that each planet produces a kind of music as it moves, a tone determined by the speed of its orbit. Jupiter and Saturn played slow, deep notes. Mercury and Venus sang higher, faster ones. To Kepler, the solar system was a choir, each planet contributing to a cosmic song. Though modern science no longer imagines literal music emerging from planets, the metaphor of harmony persists. Astronomers now know that stars oscillate and vibrate like vast instruments, their sound waves trapped within their interiors. These vibrations, though far below human hearing, can be translated into audible frequencies. The sun itself hums, producing resonances that reveal its internal structure. Distant stars, too, sing their songs studied in a field known as astroseismology. In a very real sense, the cosmos is filled with music, though we must translate its frequencies to perceive them. Beyond literal sound, the concept of cosmic harmony lies in proportion. The orbits of planets follow laws of motion that can be expressed as precise mathematical relationships. The spacing of moons, the rhythm of pulsars, the spiraling arms of galaxies, all move with a coherence that feels less like accident and more like composition. The universe is not random noise. It is structured like a symphony, with repeating motifs, crescendos, and quiet pauses. Consider the spiral. From hurricanes to galaxies, the same geometry recurs, echoing the Fibonacci sequence and the golden ratio. These spirals resemble the curves of a violin's body, the waveforms of sound, the shape of a seashell. Why should the same forms appear across such different domains? It is as if the universe has a preferred scale, a hidden rhythm that it plays again and again. Modern physics adds another dimension to this metaphor. Quantum mechanics reveals that particles, too, behave like waves, vibrating across fields of probability. Matter itself may be music at its core, each particle a note, each interaction a chord. String theory takes this further, proposing that the fundamental building blocks of reality are tiny vibrating strings, each resonance giving rise to a different particle. If true, then the universe is literally a symphony, its matter and forces born from vibrations, its existence arising from song. The emotional power of this vision is overwhelming. To imagine the cosmos as music is to imagine ourselves as part of that harmony. Every atom in our bodies vibrates, every cell pulses with rhythm, every breath falls in a cadence. Life is not separate from the music of the spheres, it is a verse within it. When we listen to music on Earth, perhaps part of what we feel is recognition, an echo of the deeper harmonies that shaped us. And yet, there is tension within this vision. Harmony suggests balance, beauty, perfection, but the universe is also violent. Stars explode in supernovae, galaxies collide, black holes consume light. Where is the harmony in destruction? Perhaps it is here that the metaphor deepens. A symphony is not only soft notes and gentle melodies. It is also dissonance, tension, and release. The universe's music is not a lullaby, but a full composition, complete with crescendos of chaos and resolutions of order. Even destruction, viewed in the grand scale, contributes to the ongoing song. Supernovae scatter heavy elements, seeding the cosmos with the materials for planets and life. Dissonance creates possibility. Philosophers have long wrestled with whether this harmony implies design. If the universe is music, does that mean there is a composer? Or is harmony the inevitable outcome of mathematics, with no need for intention? To some, the elegance of cosmic ratios feels too perfect to be mere accident, as though an architect tuned the strings of existence with deliberate care. To others, harmony is simply the natural result of laws unfolding, beauty arising not from intention, but inevitability. And yet, when we gaze at the stars or listen to the translated hum of distant suns, the experience feels transcendent. We are reminded that we are not separate from the cosmos, but participants in its harmony. Our thoughts, our emotions, our creations, these too are notes in the greater symphony. Perhaps the architects of the universe did not simply build a machine, but composed a song that continues to echo across time and space, a song in which every being, every planet, every galaxy plays a part. The music of the spheres is not silence. It is the whisper of order within chaos, the song of proportion and rhythm, the resonance of existence itself. And whether by design or by law, it reminds us that the cosmos is not void but voice, not random but resonant, not mute but melodic. It is a song we cannot escape because we are made of its notes. Throughout history, the human spirit has been captivated by the desire to uncover order in the cosmos. The night sky, vast and scattered with countless stars, has always suggested a tension between chaos and design. Ancient civilizations believed that the heavens were not random but purposeful, guided by divine will or celestial law. The Babylonians mapped the motions of the planets with extraordinary precision, convinced that their alignments foretold events on Earth. The Egyptians oriented their pyramids with stellar accuracy, linking eternity with the constellations. The Mayans, too, embedded their temples within celestial calendars, believing that cosmic order was the foundation of earthly life. Philosophers elevated this search to a metaphysical quest. For Plato, the cosmos was an expression of harmony, constructed by a divine craftsman who shaped chaos into order. Aristotle sought to categorize the heavens into perfect spheres, each moving with flawless precision. These early frameworks were not only scientific in ambition, but deeply spiritual. They suggested that the universe was intelligible, governed by rules that human reason could discover. To seek cosmic order was in essence to seek meaning itself. As centuries passed, the search for order grew more mathematical. Euclid, Archimedes, and other mathematicians revealed that geometry was not merely abstract thought, but the hidden language of reality. Circles, triangles, and ratios became metaphors for the eternal laws that shaped the stars. The Pythagorean notion that all is number became a guiding principle for generations of thinkers. To chart the heavens was to read the code of creation, to glimpse the architecture of the divine. This pursuit reached a climax in the Renaissance, when Copernicus dared to reposition the Earth. By placing the sun at the center, he restored elegance to the movements of the heavens. Suddenly, the erratic paths of the planets became ordered, their loops and retrogrades dissolving into simple, graceful ellipses. Galileo extended this vision, pointing his telescope at the night sky and discovering that the moon was not a smooth sphere but a rugged world, that Jupiter had moons of its own, and that the universe was far more complex and ordered than tradition had imagined. The search for order was no longer a purely philosophical exercise. It was becoming a scientific revolution. Kepler, driven by a near-mystical belief in cosmic harmony, sought patterns in planetary motion. He abandoned the ancient idea of perfect circles and uncovered instead the elliptical orbits that governed the solar system. These discoveries were not just empirical but aesthetic. Kepler believed that mathematical precision reflected the beauty of creation. Newton then distilled these insights into universal law, showing that the same force that made an apple fall to earth bound the planets in their courses. The heavens and the earth were no longer separate realms. They were unified by the same principle of gravity. For the first time, order was revealed as universal, comprehensible, and predictive. Yet even as science deepened our grasp of cosmic order, it also complicated it. The Enlightenment philosophers celebrated the universe as a grand clockwork, precise and mechanical. But the Romantic poets and mystics resisted this cold vision, insisting that order was not merely mechanical, but also spiritual and emotional. To them, the stars sang a wonder, not just law. Cosmic order was more than equations. It was an invitation to awe, to humility, to reverence. In the 20th century, the search for cosmic order entered new and paradoxical terrain. Einstein's theory of relativity revealed that space and time themselves were elastic, curved by gravity, woven together into a fabric that defied old intuitions. The order of the universe was deeper than Newton had imagined, yet also stranger. Simultaneously, quantum mechanics unveiled a subatomic world governed by probability, uncertainty, and paradox. At one scale, the universe appeared precise and deterministic. At another, it shimmered with indeterminacy. The search for order had not ended. It had fractured into layers of reality, each with its own rules. Even now, scientists and philosophers wrestle with the question, is the universe fundamentally ordered, or is order only an illusion our minds impose upon chaos? Chaos theory itself complicates the picture, showing how deterministic systems can produce unpredictable outcomes, how simple rules can yield complexity beyond comprehension. Yet hidden within chaos are patterns, fractals, strange attractors, self-similarity, that suggest that order and disorder are not opposites, but partners in creation. Perhaps this is the greatest lesson of the search for cosmic order, that what appears chaotic on one scale may be ordered on another, and that the universe contains a hierarchy of patterns, each revealed only through the right lens. From the spiral of a galaxy to the rhythm of a heartbeat, from the orbit of a planet to the swirl of a storm, order emerges in endless guises. For humanity, the pursuit of cosmic order has always been more than scientific curiosity. It is existential. To uncover order is to reassure ourselves that the universe is not indifferent, that we belong within a structure that can be understood. The stars become not just distant fires, but symbols of coherence, reminders that existence itself is woven into a fabric of meaning. Even when faced with the immensity of the unknown, the human mind refuses to surrender to chaos. It seeks rhythm, pattern, law, because to discover order in the cosmos is to discover it in ourselves. For centuries, humanity believed that the universe we see, the galaxies, stars, planets, and space between them, was all that existed. Even as telescopes revealed deeper layers of the cosmos, even as science unveiled billions of galaxies stretching into the dark, The underlying assumption remained the same. There is one universe, and it is singular. But modern physics has begun to fracture that assumption, opening a door to one of the most mind-bending possibilities ever imagined. That ours is but one of countless universes, a single bubble in a vast multiverse. The roots of this idea emerge not from speculation alone, but from the equations of cosmology and quantum theory. In the early 20th century, Einstein's theory of relativity revealed that space and time were not passive backdrops, but dynamic, stretching and curving with energy. Then, in the 1920s, astronomer Edwin Hubble discovered that galaxies were racing away from us, suggesting the universe was expanding. If we trace that expansion backward, we arrive at a singular beginning, the Big Bang. Yet this explanation, so elegant and powerful, raises troubling questions. Why did the Big Bang happen at all? Why were the initial conditions so fine-tuned for the emergence of life? Inflation theory, proposed in the 1980s, sought to address these mysteries. According to this model, the universe underwent an unimaginably rapid expansion in the tiniest fraction of a second after the Big Bang, stretching space-time smooth and uniform. But inflation may not be a one-time event. Some versions of the theory suggest that inflation is eternal, spawning bubble after bubble of space-time, each a universe unto itself. Our cosmos, then, might be only one of countless others, floating like foam upon a cosmic sea. This concept, known as the multiverse, reshapes the very meaning of reality. In one version, every bubble universe may have its own physical constants, laws of nature, and dimensions of space and time. Some may be barren voids, collapsing almost as soon as they form. Others may blaze with stars, but lack the chemistry to produce life. And a rare few, perhaps ours among them, may possess just the right balance of forces to allow galaxies, planets, and conscious beings to arise. If true, the multiverse offers a radical answer to one of science's deepest riddles: why the universe seems so finely tuned for life. We exist here not because the cosmos was designed for us, but because in a vast ensemble of universes, only certain ones allow observers to exist at all. Quantum mechanics, too, pushes toward a multiverse vision. At the smallest scales of reality, particles behave in ways that defy common sense, existing in multiple states until observed. To make sense of this, physicist Hugh Everett proposed the many-worlds interpretation in the 1950s. In this view, every quantum event doesn't resolve into one outcome, but branches into many, creating parallel realities where every possibility is realized. In one world, you make a certain choice. In another, you choose differently. The universe doesn't collapse possibilities into one path. It proliferates them endlessly. This quantum multiverse suggests that reality is far richer and stranger than our perceptions allow. For philosophers, the multiverse is both exhilarating and unsettling. On one hand, it dissolves the uniqueness of our cosmos, transforming it into just one island among infinite shores. On the other, it challenges our notions of significance. If infinite universes exist, then infinite versions of you may also exist, living out every imaginable variation of your life. Does this make your choices less meaningful? Or does it make the fact of this particular existence even more precious? Science, however, demands evidence. And here lies the challenge. By definition, other universes may be beyond our reach, sealed off by horizons of space and time. Yet physicists search for indirect clues. The cosmic microwave background, the faint afterglow of the Big Bang, might contain subtle imprints of collisions between bubble universes. Certain patterns in the distribution of galaxies might hint at gravitational effect from other cosmic realms. Though unproven, these possibilities push researchers to design ever more sensitive instruments, searching for whispers from beyond our own universe. The multiverse also collides with deep philosophical debates about the nature of science itself. Can an idea be considered scientific if it cannot be directly tested? Critics argue that the multiverse drifts dangerously close to metaphysics. Supporters counter that if the multiverse arises naturally from well-tested theories, such as inflation or quantum mechanics, then to deny it would be to ignore where the equations lead. The argument itself reflects the tension at the heart of modern cosmology. Are we uncovering the true architecture of existence, or are we staring into a hall of mirrors constructed by our own mathematical imagination? Despite the uncertainties, the multiverse has captured the popular imagination. Films, novels, and art now explore its implications, from alternate timelines to parallel Earths where history unfolded differently. These cultural expressions reflect our longing to escape the limits of a single destiny, to imagine that somewhere out there exists another version of ourselves who made different choices, lived different lives. The multiverse, whether real or not, serves as a metaphor for possibility itself. Yet the question lingers: if infinite universes exist, what does that mean for meaning itself? Some argue that the multiverse strips our lives of uniqueness, rendering us mere repetitions in an endless sea. Others see the opposite. In a cosmos so vast, the fact that we are here, now, in this moment, conscious of our existence, is nothing short of miraculous. The multiverse does not diminish wonder. It amplifies it, reminding us that reality is deeper than we can possibly imagine. The rise of the multiverse marks a profound shift in human thought. It expands our perspective from one universe to many, from a finite stage to an infinite theater. It confronts us with the possibility that reality is not singular but layered, proliferating, endlessly diverse. And in doing so, it challenges us to reconsider what it means to exist at all. Are we the products of chance, of infinite cosmic rolls of the dice? Or are we participants in a grander pattern, one whose scale defies comprehension? For now, the multiverse remains a theory at the edge of science, a vision that stretches imagination as much as mathematics. But whether it is ultimately proven or not, its very conception reshapes the way we see ourselves and the cosmos. It reminds us that mystery still pulses at the heart of reality, that even as our instruments grow sharper, there will always be horizons beyond. And perhaps that is the truest order of the universe, that it forever calls us to seek, to question, to wonder what lies beyond the veil of the known. From the first flicker of the Big Bang to the delicate emergence of galaxies, stars, and life itself, the universe appears to be balanced on a razor's edge. The laws of physics, the values of fundamental constants, and the initial conditions of cosmic expansion are tuned with extraordinary precision. A shift in any one of them, by even the smallest fraction, could have rendered the cosmos barren, collapsing back into itself or expanding too rapidly for stars to form. This uncanny balance has become one of the most profound puzzles in modern science. The cosmic fine-tuning problem. Consider the force of gravity. If it were slightly stronger, matter would have collapsed too quickly after the Big Bang, forming massive black holes instead of galaxies. If it were slightly weaker, the universe would have expanded so rapidly that stars and planets could never take shape. The strength of gravity rests at a value so exact it defies coincidence. Likewise, the electromagnetic force governs chemistry, bonding atoms into molecules. Had it been just a little different, the complexity of life, the very structures that compose our bodies, could not have emerged. The fine-tuning extends even deeper. The ratio of the proton to electron mass, the strength of the strong nuclear force that binds atomic nuclei, the cosmological constant that drives the expansion of the universe. All of these sit within narrow ranges that permit the existence of stars, elements, and ultimately, observers. Change them slightly, and the universe becomes unrecognizable. The cosmological constant is especially striking. Its measure value is staggeringly small compared to what theory predicts. If it were even a fraction larger, the accelerated expansion of the universe would have torn apart galaxies before they could form. Its precise value seems almost impossibly tailored for life. This raises a haunting question. Why does the universe appear fine-tuned for existence? One answer appeals to sheer chance, that we happen to live in a universe where conditions align, even if the odds are astronomically low. Another perspective, often associated with the anthropic principle, argues that we should not be surprised by fine-tuning, because only in such a universe could conscious beings arise to ask the question. Out of a vast landscape of possibilities, we find ourselves here simply because no other outcome allows us to exist. But for many scientists and philosophers, these answers feel incomplete. Chance alone struggles to account for such precise alignment, and the anthropic principle, while logically consistent, offers little in the way of deeper explanation. This tension has opened the door to theories like the multiverse. If countless universes exist, each with different values of physical constants, then it is not surprising that one, ours, happens to be fine-tuned for life. We are here because in a cosmic lottery of infinite outcomes, only certain winning tickets produce observers. Yet the multiverse explanation itself raises new questions. If universes are infinite, does fine-tuning lose its mystery, reduced to inevitability? Or does invoking infinite worlds simply shift the puzzle to a higher level, demanding an explanation for why the multiverse itself exists? In trying to answer one riddle, we may only be deepening another. Some thinkers entertain the possibility that fine-tuning reflects not chance, but design. This perspective suggests that the constants of nature were intentionally set, that the cosmos is not a random accident, but a purposeful construction. To some, this echoes ancient traditions of a cosmic architect or divine order. To others, it feels like an unnecessary leap, invoking explanations beyond the reach of science. Still, the allure of intentionality lingers, for the precision of fine-tuning evokes the craftsmanship of something greater than blind chance. Another approach proposes that what we see as fine-tuning may eventually dissolve under a deeper understanding of physics. Perhaps the constants are not arbitrary at all, but necessarily follow from fundamental laws we have yet to uncover. If gravity, electromagnetism, and quantum mechanics all arise from a single unified framework, then their apparent tuning might not be surprising but inevitable. In this view, fine-tuning is a temporary illusion born of incomplete knowledge. For now, however, the fine-tuning problem stands as both a scientific and philosophical challenge. It confronts us with the improbability of our own existence, demanding explanation yet eluding certainty. Is the universe a lucky accident, one of many in an infinite sea? Is it the product of necessity, guided by hidden principles? Or is it something more profound, hinting at an architecture we cannot yet grasp? The emotional impact of fine-tuning is undeniable. To reflect upon the fragility of existence is to feel awe, perhaps even fear, at how easily it all could have been otherwise. The stars, the earth, our bodies, our very thoughts, all of it depends on balances so exact that they seem miraculous. And yet here we are, conscious beings gazing into the abyss, able to ponder the mystery of why the cosmos is as it is. Whether the fine-tuning problem is eventually solved by science, philosophy, or remains an eternal enigma, it reminds us of a fundamental truth. Existence itself is precarious and precious. Every breath, every moment of awareness, every glimpse of the night sky testifies to the delicate harmony that sustains us. To question fine-tuning is to stand at the edge of wonder, where science and mystery converge, and where the universe whispers its secrets through the narrowest margins of possibility. At first glance, the universe seems like a cascade of chance. Stars explode without warning, galaxies collide in chaotic swirls, and on our own planet, life emerges from the unpredictable interplay of chemistry and time. We look at the roll of dice, the shuffle of cards, the sudden storm that appears on a clear day, and we declare randomness. But what if randomness itself is only an illusion? What if beneath the chaos lies an unseen pattern, a hidden order too subtle for our minds to grasp? This is the mystery that has haunted both science and philosophy for centuries. Is the cosmos truly random, or is randomness merely the shadow of a deeper structure? For much of history, randomness was synonymous with ignorance. When people could not predict an outcome, they called it chance. A lightning strike, a harvest destroyed by flood, a sudden illness, all were attributed to fate or the whims of gods. But as science advanced, it revealed that many of these events followed laws. Weather patterns obey physics, diseases follow biological pathways, and even dice, if rolled with precise knowledge of initial conditions, could in principle be predicted. What once looked random began to appear as complexity, systems too intricate to calculate, but not fundamentally without order. In the 20th century, however, science encountered a deeper puzzle. Quantum mechanics, the theory describing the subatomic world, suggested that at the smallest scales of reality, chance is not just a mask for ignorance. It may be woven into the fabric of existence itself. According to the standard interpretation, particles do not have definite properties until observed. An electron is not here or there, but exists in a superposition of possibilities. Only when measured does it choose an outcome, and which outcome occurs is fundamentally random. No hidden variables, no deeper clockwork, just pure probability. This was a shocking departure from centuries of deterministic thought. Yet not everyone accepts this interpretation. Einstein famously protested, "God does not play dice with the universe." He suspected that what appeared random was only a veil, concealing laws we had not yet uncovered. Others embraced the strangeness, arguing that the randomness of quantum events is real and irreducible. The debate continues to this day, with experiments probing whether quantum uncertainty is ultimate or if hidden order still lurks beneath. Beyond quantum mechanics, randomness also appears in the grander scales of nature. Evolution by natural selection thrives on variation and chance mutations. The fate of species often hinges on accidents of environment. Asteroids striking Earth, climate shifts, or random genetic drift. From this randomness, life diversifies and complexity blooms. Yet even here, the illusion of randomness reveals itself. While mutations occur unpredictably, the process of natural selection is profoundly non-random, guiding life toward forms that survive and adapt. Chaos and order dance together. Chance provides the raw material, law shapes the outcome. Chaos theory takes this paradox further. Developed in the latter half of the 20th century, chaos theory showed that deterministic systems, those governed by strict rules, can nonetheless produce outcomes that look utterly random. A tiny difference in initial conditions can lead to radically divergent results, a phenomenon often described as the butterfly effect. The flapping of a butterfly's wings in Brazil, in theory, could set off a tornado in Texas. The system is not random, but its sensitivity makes prediction nearly impossible. Here, randomness is a matter of perspective. The pattern exists, but it lies beyond our capacity to trace. Even mathematics reveals the strange boundary between order and chance. Random number generators, used in computer simulations and cryptography, rely on processes designed to mimic true randomness. But no sequence is truly patternless. Mathematicians can find structure even in apparent noise. Numbers themselves hold mysteries. Prime numbers, distributed in ways that seem irregular, follow statistical laws at large scales. What seems random up close often reveals structure from afar. This interplay between chaos and order also appears in human experience. Consider music. Random notes played without pattern create noise, but when structured into rhythm and melody, they become song. Or consider language. Random letters are meaningless, but arranged in patterns, they convey thought. Our minds are wired to seek patterns, to find order even where none exists. This tendency is so strong that we often see shapes in clouds, hear voices in static, or read meaning into coincidences. We mistake randomness for intention, and, sometimes, intention for randomness. The boundary blurs, and reality becomes a mirror of our interpretations. Philosophers have long grappled with the implications of randomness. If the universe is truly random, what does that mean for meaning, purpose, or destiny? If our lives are the products of chance, do our choices matter, or are they swallowed in a sea of probability? Some argue that randomness strips existence of significance, reducing life to a cosmic accident. Others counter that randomness creates freedom, carving out space for novelty, creativity, and evolution. Without randomness, perhaps life would be static, unchanging, devoid of the spark that allows growth and transformation. There is also the possibility that randomness is only a feature of perception. Just as ancient farmers mistook weather for fate, perhaps we mistake complexity for chance. A universe infinite in scale and layered in laws may always exceed our comprehension. What looks random to finite minds may, in truth, be the unfolding of patterns too vast to see. In this light, randomness is not the absence of order, but the shadow of a higher order concealed from view. The illusion of randomness forces us to confront the limits of knowledge. We yearn for certainty, for a universe governed by laws we can understand and predict. Yet the deeper we look, the more reality slips between order and chance, as though the cosmos is teasing us with riddles. Are we uncovering the ultimate architecture of existence? Or are we trapped in a hall of mirrors, mistaking reflections for truth? And yet, perhaps it does not matter whether randomness is real or illusory, for within it lies the source of mystery, creativity, and awe. The fact that we can roll dice, gaze at the stars, or question the unpredictability of life reveals something extraordinary. We are conscious beings capable of reflecting on chaos itself. In a universe that may or may not be random, our awareness becomes a point of order, a flame of meaning flickering in the dark. In the end, the illusion of randomness may not be a puzzle to solve, but a truth to embrace. It is the space between certainty and chaos where possibility thrives. It is the dance of order and chance that makes existence rich, unpredictable, and alive. Whether randomness is real or a mask, it reminds us of our place in the cosmic story, not as passive spectators, but as seekers, forever chasing the hidden patterns that give the universe its shape. Imagine a vast, invisible tapestry stretching in every direction, a cosmic fabric that bends, twists, and ripples beneath the galaxies, stars, and planets. This is space-time, the stage upon which the entire universe unfolds. It is not merely an empty void or a passive backdrop. It is an active, dynamic medium that shapes reality itself. Time flows, distances stretch and compress, and gravity is not simply a force but a curvature in this fabric. To understand space-time is to glimpse the very skeleton of existence, the hidden scaffolding upon which all matter and energy hang. Albert Einstein revolutionized our understanding of space-time with his theory of general relativity. Before Einstein, gravity was seen as a force pulling objects together across empty space, a kind of invisible string tugging at planets and apples alike. Einstein proposed something far more profound. Massive objects do not pull through space. They bend space and time around them. Imagine placing a heavy ball on a trampoline. The fabric dips under its weight. Roll a smaller ball nearby, and it spirals inward, not because it is attracted by a force in the traditional sense, but because the curvature of the trampoline guides its path. In this analogy, planets orbit stars not because of an unseen tug, but because they follow the curves in space-time itself. This insight was not just poetic, it was predictive. Einstein's equations could explain the precession of Mercury's orbit, the bending of starlight by gravity observed during solar eclipses, and eventually, the expansion of the universe itself. Space-time was revealed as a living structure, flexible and responsive, capable of transmitting energy and information in ways previously unimaginable. Gravity waves, ripples in the very fabric of reality, were predicted decades before their detection in 2015, when LIGO observed the collision of black holes sending tremors through space-time, like stones tossed into an invisible cosmic pond. Space-time is also intimately tied to time itself. Time is no longer absolute, ticking uniformly for all observers. It is relative, stretching, and contracting depending on velocity and gravity. Near a massive object like a black hole, time slows, a phenomenon known as time dilation. This is not theoretical fancy. It has been confirmed experimentally with precise atomic clocks on Earth and in orbit. The closer a clock is to Earth's surface, the slower it ticks compared to one further away. In extreme conditions, time itself becomes elastic, folding in upon itself. To exist in the universe is to inhabit this fluid, ever-shifting river of space-time, where the past, present, and future are intertwined rather than fixed. Black holes offer one of the most dramatic illustrations of space-time's power. A black hole is a region where matter has collapsed so densely that it creates a singularity, a point where space-time curvature becomes infinite, and the laws of physics, as we know them, break down. Surrounding this singularity is the event horizon, a boundary beyond which nothing, not even light, can escape. Space-time is stretched to extremes, warped into forms that challenge human intuition. To fall toward a black hole is to experience gravity so intense that time slows to a crawl. Space is contorted, and the very essence of reality feels fluid. These cosmic engines are not just destructive. They're laboratories for understanding the limits of existence. The interplay of space-time and energy is further revealed in the structure of the universe itself. Galaxies are not merely islands of stars. They trace the contours of space-time, clustering along filaments and voids shaped by the gravitational influence of dark matter. Invisible to our eyes, dark matter is a key component of the cosmic web, bending space-time and guiding the formation of galaxies. Without this hidden scaffolding, the universe we know, the stars, planets, and ultimately life, could not have emerged. Space-time, dark matter, and energy are woven together in an intricate cosmic dance. Time's arrow, why it moves in a single direction, is also a consequence of space-time structure. Entropy, the measure of disorder, tends to increase, giving a sense of forward motion. Yet in Einstein's equations, past and future are treated symmetrically. The unidirectional flow we experience is tied to thermodynamic conditions, yet it is inseparable from the geometry of space-time. The cosmos is a story unfolding along this river, each moment flowing from curvature, energy, and the relentless march of entropy. Space-time also challenges our notions of locality and separation. Quantum mechanics suggests that particles can be entangled, instantaneously influencing one another across vast distances. While this does not allow faster-than-light communication, it hints at a deeper connectedness embedded within the structure of reality. Space-time may not be a mere container for matter. It could be an emergent property, arising from relationships between quantum entities, woven together by the interactions that constitute existence itself. Philosophically, the malleability of space-time invites profound reflection. We are not passive observers of an indifferent stage. We move through a living medium that bends, stretches, and responds. The universe is not simply out there. It is an intimate partner in our experience, defining the contours of what is possible, guiding the motion of matter, and shaping the flow of time itself. To understand space-time is to confront the foundations of reality and our own place within it. Even cosmology, the study of the universe as a whole, depends on space-time. The Big Bang was not an explosion into empty space, but a rapid expansion of space-time itself. Galaxies are carried along this expansion, receding from one another not because they are moving through space, but because space itself is stretching. Dark energy, the mysterious force accelerating this expansion, may be a property of space-time, an intrinsic energy field pervading the cosmos. The structure and destiny of the universe are inseparable from the geometry of space-time. Ultimately, space-time is both familiar and alien. It is the framework within which we live every second, yet it stretches and curves beyond human perception. Its fabric underlies every cosmic event, from the gentle orbit of a planet to the violent merger of black holes. It is the medium through which reality manifests, the invisible stage upon which the universe performs its endless dance. To comprehend space-time is to glimpse the architecture of existence itself, to understand that everything we see, feel, and experience is inseparable from this living, flexible, and mysterious continuum. Beneath the dazzling lights of stars, beyond the spiral arms of galaxies, and hidden deep within the heart of matter itself, the universe is governed by invisible forces. These forces, unseen yet omnipresent, shape everything from the orbits of planets to the chemistry of life, from the collision of galaxies to the behavior of subatomic particles. Gravity, electromagnetism, and the strong and weak nuclear forces are the architects of reality, the hidden hands that mold the cosmos with precision and power. To understand them is to glimpse the deep rules that govern existence itself. Gravity is perhaps the most familiar of these forces, yet its reach is astonishing. It binds the cosmos together, holding planets in orbit around stars and stars within galaxies. Isaac Newton's law of universal gravitation provided the first mathematical understanding, describing how masses attract each other with a force inversely proportional to the square of the distance between them. This simple equation explains a staggering range of phenomena, from the tides on Earth to the motion of distant comets. Yet even Newton could not have imagined the deeper reality Einstein would later reveal. Gravity is not a force transmitted across space, but a curvature of space-time itself. Massive objects bend the fabric of the cosmos, guiding the motion of everything around them. Gravity is both subtle and profound, silent yet omnipotent. Electromagnetism, in contrast, governs the visible world. It binds electrons to nuclei, forming atoms, molecules, and the chemistry that makes life possible. It allows light to travel across space, carrying information from distant stars to our eyes and telescopes. Electromagnetism shapes the auroras that dance over polar skies and the storms that rage in planetary atmospheres. It is the force behind electricity, magnetism, and light, the very tools we use to explore the universe. Without it, matter as we know it would not exist. Without it, there would be no chemistry, no life, no vision. The strong nuclear force, by contrast, operates at an almost inconceivably small scale, holding protons and neutrons tightly together within atomic nuclei. Without it, the universe would be a sparse cloud of subatomic particles. Atoms would disintegrate before they could form molecules. The strong force is the glue of matter, a concentrated, powerful bond that allows stars to fuse hydrogen into helium, producing the energy that lights the cosmos. Every photon of sunlight, every element heavier than hydrogen, owes its existence to the intense embrace of the strong nuclear force. Complementing this is the weak nuclear force, subtle yet essential. It governs radioactive decay, transforming one type of particle into another, enabling nuclear reactions that power stars and create the building blocks of life. Without the weak force, the sun could not fuse hydrogen into helium efficiently, and elements like carbon and oxygen would never form in the hearts of stars. The weak force operates quietly behind the scenes, yet its influence resonates across the cosmos, from the birth of stars to the emergence of life itself. These four forces, together, create a universe capable of complexity, diversity, and wonder. Yet their balance is delicate. Change the strength of anyone, even slightly, and the universe would be unrecognizable. A stronger gravity would cause stars to burn out too quickly. A weaker electromagnetic force would prevent atoms from forming. A stronger strong force would collapse matter into impossibly dense states. A weaker weak force would halt the nuclear reactions that synthesize essential elements. The cosmos exists within a narrow corridor of possibility, a precarious equilibrium maintained by these hidden forces. Modern physics has revealed even stranger dimensions to these forces. Quantum field theory describes particles not as solid objects, but as excitations in underlying fields that permeate space-time. Every photon is a ripple in the electromagnetic field, every gluon a vibration in the strong force field. Forces are carried by particles, messengers that transmit influence across the void. The universe is alive with activity at scales far smaller than atoms, a ceaseless interplay of fields and quanta that orchestrates reality with elegance and precision. Then there is dark matter, a mysterious substance that outweighs visible matter by a factor of 5, yet interacts primarily through gravity. Though invisible to telescopes, its presence is inferred from the motion of stars and galaxies and the bending of light through gravitational lensing. Dark matter sculpts the cosmic web, guiding the formation of galaxies and clusters. Without it, the universe would be a very different place, chaotic and formless. Its hidden influence hints at forces and entities we have yet to fully comprehend, a reminder that the universe still conceals vast secrets. Even more enigmatic is dark energy, the force accelerating the expansion of the cosmos. Discovered through observations of distant supernovae, dark energy counteracts gravity on the largest scales, stretching space itself. It makes up roughly 70% of the universe, yet its nature remains one of the greatest mysteries in science. It is as if the universe carries an invisible hand, gently pushing galaxies apart, shaping the ultimate destiny of all cosmic structures. Understanding dark energy may require a revolution in physics, a glimpse into layers of reality beyond our current theories. The hidden forces of the universe are not merely abstract concepts. They're the engines of existence, shaping every star, planet, and living organism. They operate across unimaginable scales, from the heart of an atom to the cosmic web of galaxies. Their interplay creates the patterns we see, the beauty we experience, and the complexity that allows consciousness to emerge. These forces are silent, invisible, yet profoundly intimate. They govern the particles in our bodies, the air we breathe, and the orbit of the Earth around the Sun. Philosophically, the hidden forces provoke awe and humility. They remind us that the universe is not arbitrary, but structured, ruled by principles that we can glimpse yet never fully grasp. To understand them is to witness the blueprint of existence, the invisible architecture that underlies everything. And to ponder their subtlety and power is to recognize our own fragility and wonder. We live in a universe shaped by forces we cannot see, but upon which everything depends. A cosmos where the invisible reigns supreme and where every moment, every heartbeat, is orchestrated by the silent hands of nature. Beneath the apparent solidity of the world lies a domain stranger than any dream, the quantum realm. Here, particles do not follow predictable paths. Objects can exist in multiple states at once, and reality itself seems to defy logic. The universe at this scale is not continuous and smooth, but jagged, probabilistic, and vibrating with possibility. This is the quantum fabric of reality, a hidden layer of existence that challenges our understanding of space, time, and even causality itself. To explore it is to confront a reality that is at once incomprehensible, beautiful, and deeply unsettling. Quantum mechanics emerged in the early 20th century to explain phenomena that classical physics could not. The behavior of light, the stability of atoms, and the discrete energy levels of electrons revealed a world fundamentally different from everyday experience. Max Planck, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the mathematical framework that describes this universe, a realm where particles are waves, probabilities replace certainties, and measurement alters reality. At its heart, quantum mechanics shows that the universe is not a clockwork machine, but a tapestry of possibilities, constantly collapsing into outcomes that we perceive as real. Perhaps the most famous illustration of quantum strangeness is the double-slit experiment. When particles such as electrons are fired at a barrier with two slits, they behave like waves, creating interference patterns, unless observed, in which case they behave like particles striking one slit or the other. Reality, it seems, is shaped not only by laws but by observation. Schrödinger's cat, alive and dead at once until the box is opened, captures the unsettling paradox. The quantum world is probabilistic until it interacts with the classical world. The boundaries of reality are blurred, and certainty dissolves into possibility. Entanglement adds yet another layer of mystery. Two particles can become linked so that the state of one instantaneously affects the other, regardless of distance, a phenomenon Albert Einstein calls spooky action at a distance. Measurements performed on one particle reveal information about the other, as if the universe maintains a hidden network connecting everything at a fundamental level. This entanglement challenges our notions of locality and separateness, suggesting that at its core, reality may be far more interconnected than we imagine. Quantum fields, the foundation of particle physics, extend this strange logic. Particles are not independent points, but excitations in underlying fields that permeate all space. Electrons are ripples in the electron field, photons vibrations in the electromagnetic field. Forces arise from interactions between these fields, giving rise to the fundamental structure of the universe. The cosmos is not composed of isolated entities, but a continuous web of energy, resonance, and fluctuation. Every particle, every photon, every quark is a manifestation of this quantum fabric, a note in the symphony of existence. The probabilistic nature of quantum mechanics also has profound implications for causality. In classical physics, causes lead to effects with certainty. In the quantum realm, outcomes are only probable. This does not mean that everything is random. Patterns emerge over time, governed by probabilities, but it challenges deterministic assumptions. The universe at its foundation is not rigid. It is flexible, responsive, and fundamentally uncertain. Chance is woven into the laws themselves, making the cosmos a delicate dance between order and unpredictability. This strangeness extends to the very fabric of space-time. Quantum fluctuations, tiny variations in energy that occur even in empty space, give rise to ephemeral particles that blink into and out of existence. These fluctuations may have shaped the early universe, seeding the density variations that would grow into galaxies. Some theories suggest that the vacuum of space is not nothing but a roiling quantum sea, alive with virtual particles and energy, a background hum upon which the cosmos is painted. Space-time, then, is not smooth but granular, a lattice of quantum events forming the scaffolding of reality. String theory takes this even further, proposing that fundamental particles are not points but tiny, vibrating strings. Each vibration corresponds to a different particle, and the interactions of these strings give rise to all forces and matter. In this vision, the universe is literally made of resonance, a symphony of vibrations underlying every aspect of existence. Dimensions beyond our perception may exist, curled up at scales far smaller than atoms, shaping the physics we observe without ever being directly visible. The quantum fabric is rich, multidimensional, and intricate beyond comprehension. The philosophical implications of quantum mechanics are profound. Free will, determinism, and the nature of reality itself come into question. If outcomes are probabilistic, then perhaps the universe is not predetermined, leaving room for novelty, choice, and creativity. If observation affects reality, consciousness may play a subtle role in shaping existence, a notion that continues to spark debate among scientists and philosophers alike. The quantum realm forces us to confront the limits of human intuition, revealing that the universe operates according to principles that our everyday experiences can only hint at. Quantum mechanics also humbles us with its scale. Though its effects are most apparent at the subatomic level, the consequences ripple upward, The stability of matter, the fusion of stars, the chemistry of life, all depend on quantum laws. The world we see and touch, solid and predictable, emerges from this underlying quantum sea. Every object, every interaction, every photon of light carries the imprint of this hidden realm, reminding us that beneath apparent reality lies a universe far stranger and more wondrous than our senses suggest. To peer into the quantum fabric of reality is to glimpse the universe as a complex interplay of energy, probability, and connection. It is to recognize that certainty is limited, that the world is alive with possibility, and that the boundaries between existence and potentiality are not fixed. Here, at the heart of nature, we encounter mystery and beauty intertwined, chaos and order dancing together. The quantum realm is both the foundation and the frontier of reality, a place where the universe reveals itself as simultaneously strange, intricate, and profoundly alive. Every pattern in the cosmos, from the spiral of galaxies to the intricate structures of molecules, hints at an underlying architecture. The universe is not chaotic formlessness. It is a vast construction shaped by laws, forces, and structures that act as its architects. But who, or what, are these architects? In the realm of physics and cosmology, they are the principles and mechanisms that govern reality. The hidden forces, quantum laws, and cosmic patterns that orchestrate existence with astonishing precision. To study them is to peer into the blueprint of the cosmos itself. From a moment of the Big Bang, these architects began their work. The initial conditions of the universe, seemingly random, conspired to create the possibility of complexity. Tiny quantum fluctuations, invisible to the naked eye, seeded the formation of galaxies. Gravity acted as a sculptor, pulling matter together, shaping stars, and guiding planets into stable orbits. Electromagnetism allowed atoms to bond, forming the chemistry necessary for life. The strong and weak nuclear forces powered stars, created the elements, and enabled the energy flows that sustain galaxies. Each force played a precise role, as if following a master plan hidden in the fabric of reality. Mathematics itself appears as a language of these architects. Patterns, ratios, symmetries, and geometries are embedded throughout the cosmos. The Fibonacci sequence emerges in spiraling galaxies and seashells. The golden ratio appears in the proportions of natural forms. Prime numbers, fractals, and wave patterns hint at a universe constructed with an intrinsic sense of order. Some scientists argue that these mathematical structures are not human impositions, but reflect the fundamental logic of existence. The universe is written in numbers, and to decode, it is to read the handwriting of its architects. Quantum mechanics further complicates the picture. Particles and waves, probabilities and entanglement, all operate under strict rules that are counterintuitive yet consistent. These rules dictate the architecture of reality at its smallest scales, shaping matter and energy into forms that cascade upward into complexity. The quantum world is not random chaos. It is an ordered, probabilistic network, guiding the emergence of stars, planets, and ultimately life. The architects operate invisibly here, yet their influence is omnipresent, structuring the building blocks of everything we see. Cosmology suggests that the architects extend beyond the visible universe. Dark matter and dark energy, which together comprise the majority of the cosmos, guide its evolution. Dark matter forms the scaffolding for galaxies, unseen yet critical. Dark energy drives the expansion of space-time, determining the universe's ultimate fate. Without these hidden agents, the cosmos would be radically different, fragmented, chaotic, or lifeless. Even as our instruments detect only the faintest traces, the influence of these architects is undeniable, shaping reality on the grandest scales. Some theorists suggest that the universe is part of an even larger framework, perhaps a multiverse, where countless other realities are being constructed simultaneously. Each universe may follow its own laws, its own hidden architects, leading to infinite variations of cosmic structure. In such a vision, the architects are not unique but manifold, each creating worlds according to subtle rules, weaving diversity from a common substrate. This idea stretches imagination, proposing that the principles shaping our reality are part of a far greater cosmic design. The search for these architects is both scientific and philosophical. Scientists aim to uncover the mechanisms, the laws of physics, the constants of nature, the geometry of space-time. Philosophers ponder the implications. If the universe is structured by invisible architects, what does this mean for meaning, purpose, and consciousness? Are we merely products of impersonal forces, or do the architects hint at intention, intelligence, or design at a level beyond our comprehension? Every discovery deepens the mystery, revealing the universe as simultaneously understandable and profoundly elusive. Even at the human scale, we see evidence of these architects in subtle ways. Life itself is a complex arrangement of matter and energy obeying physical laws, yet producing consciousness, emotion, and creativity. Our ability to perceive, reason, and question may be considered an extension of the cosmic architecture, a reflection of a universe becoming aware of itself. The patterns that sustain galaxies are mirrored in the structures that sustain life, suggesting a harmony that spans scales from the quantum to the cosmic. Yet the architects are elusive, never fully revealed. Every layer of understanding exposes deeper complexity. The forces we observe, the laws we formulate, may be only a glimpse of a far greater set of principles that operate beyond space, time, or human perception. To contemplate them is to confront both wonder and humility. The universe is at once familiar and alien, its patterns reassuring yet incomprehensible, its architects both present and hidden, guiding reality in ways that defy imagination. The very act of observation, of probing the cosmos with science, can be seen as tracing the work of these architects. Each equation, experiment, and telescope captures a fragment of the blueprint. Gravity's pull, electromagnetism's bond, the probabilistic dance of particles, all are signatures of a structure that underlies the universe. By studying them, we do more than understand nature. We glimpse the invisible hands that have shaped existence since the beginning of time. In the end, the architects of reality remain partly hidden, their presence felt but their full nature unrevealed. They're the laws, the forces, the patterns, and the structures that orchestrate the cosmos, creating order from potential, shaping matter into complexity, and guiding the emergence of life. Whether impersonal or intentional, known or forever mysterious, their influence permeates every corner of the universe. To seek them is to seek understanding itself, to trace the invisible lines of cosmic design, and to stand in awe of a reality more intricate and magnificent than imagination alone can convey. As we peer deeper into the cosmos and delve further into the quantum realm, we encounter the limits of human comprehension. The universe stretches beyond the reach of our telescopes, and reality bends in ways that strain intuition. Black holes swallow light and time. Quantum particles exist in multiple states simultaneously, and dark energy drives the expansion of space faster than our minds can easily grasp. At the edge of understanding, science meets mystery, and the line between knowledge and imagination blurs. The most profound discoveries often reveal just how much we do not know. The cosmic microwave background, the afterglow of the Big Bang, encodes the earliest moments of existence. Yet interpreting its faint patterns requires extraordinary precision and abstraction. Gravitational waves ripple through space-time, carrying messages from collisions of black holes billions of light years away. Yet we must construct vast instruments like LIGO to detect these subtle tremors. Each breakthrough opens new vistas, yet simultaneously exposes the vast expanse of the unknown that lies beyond. Human perception itself is limited. We experience reality through senses attuned to a narrow range of stimuli: light, sound, temperature, and touch. Yet most of the universe exists outside these bounds. We cannot see dark matter or dark energy directly, cannot feel gravitational waves, cannot perceive quantum superpositions. To access these realms, we build tools, extend our senses with instruments, and translate the invisible into numbers, graphs, and simulations. Even so, these translations are partial, filtered through human cognition, leaving us only glimpses of the true nature of reality. Philosophers and scientists alike have grappled with the implications of these limits. If our understanding is bounded by perception, by biology, by the frameworks of mathematics and language, can we ever truly know the universe? Are our theories approximations, shadows of a deeper truth that lies beyond thought itself? Some suggest that ultimate reality may be forever inaccessible, that the universe contains layers of complexity that no finite mind can fully grasp. Yet this recognition does not lead to despair. It inspires curiosity, humility, and the relentless pursuit of knowledge. At the frontier of understanding, uncertainty becomes a tool rather than a barrier. Quantum mechanics, for instance, embraces indeterminacy as a fundamental feature, revealing patterns that emerge only in probabilities. Chaos theory demonstrates that deterministic systems can appear unpredictable, illustrating that even strict laws can produce behavior that seems random. By studying these phenomena, humans learn to navigate uncertainty, extracting order from apparent chaos and finding insight where intuition fails. The limits of understanding also highlight the role of imagination in science. Thought experiments, from Schrödinger's cat to Einstein's elevator, allow us to explore possibilities beyond direct observation. Mathematics, too, extends cognition, enabling the construction of models of space-time, black holes, and the early universe. These abstractions bridge the gap between perception and reality, providing glimpses of truths that cannot be observed directly. Human intellect, it seems, thrives not despite its limits, but because of them, using creativity to probe the infinite. Yet there's a tension at this edge. The more we know, the more questions arise. Every discovery opens new mysteries. The nature of dark energy, the origin of quantum laws, the reason the universe appears fine-tuned for life. The unknown is vast, a horizon receding as we approach, reminding us that knowledge is both power and mystery. The pursuit itself becomes a journey, not toward final answers, but toward ever deeper understanding and wonder. Emotions are entwined with cognition at this frontier. Awe, fear, and curiosity coexist as we confront the incomprehensible scale and complexity of the cosmos. Looking at a black hole or contemplating parallel universes, we experience both insignificance and connection. Our lives are fleeting, yet our consciousness allows us to ponder existence itself. The edge of understanding is a space of profound reflection, where science meets philosophy and where the human spirit grapples with the enormity of reality. Ultimately, the edge of human understanding is not a barrier, but a frontier. It defines the limits of perception and comprehension, yet invites exploration, creativity, and discovery. It reminds us that knowledge is provisional, that reality is vast and layered, and that the pursuit of truth is an endless journey. Standing here, we are both humbled and inspired, aware of our limitations, yet exhilarated by the infinite possibilities that lie just beyond reach. The universe is a stage where order and chaos perform an intricate, perpetual dance. From the smallest quantum particles to the largest galactic superclusters, every structure, every interaction, every ripple of energy reflects the tension between predictability and unpredictability. Chaos does not signify disorder, but dynamic complexity, while order does not imply stagnation, but elegant structure. Together, they form the rhythm of existence, a balance that allows the cosmos to evolve, adapt, and sustain life. At the quantum level, chaos and order are inseparable. Particles exist in probabilistic states, their behavior uncertain until measured. Yet across vast numbers, patterns emerge. Atoms form molecules, molecules form cells, and cells organize into living organisms. What seems random at first glance, quantum fluctuations, mutations, or environmental disturbances, becomes the foundation of complex, ordered systems. Life itself is born from this interplay. The chaos of mutation meets the order of natural selection, producing diversity, adaptation, and complexity over time. On larger scales, cosmic structures exhibit the same dynamic balance. Galaxies cluster along filaments, leaving immense voids in between, forming a cosmic web shaped by gravity and dark matter. Stars ignite and die, scattering elements into space, seeding future generations of solar systems. Supernovae are chaotic explosions, yet their energy fuels the formation of planets, moons, and life-supporting environments. The universe is neither static nor purely random. It is alive with motion, transformation, and emergent patterns that span space and time. Chaos theory helps us understand how deterministic systems can produce unpredictability. Tiny differences in initial conditions, a butterfly flapping its wings, or a particle's quantum fluctuation, can lead to vastly different outcomes over time. This sensitivity means that even systems governed by strict laws appear unpredictable, creating a complex tapestry where order emerges from seeming randomness. Hurricanes, planetary climates, and even economic systems display these principles, revealing that the universe's rules can produce astonishing diversity without external guidance. The dance of order and chaos also extends to human experience. Our societies, economies, and technologies emerge from countless individual decisions, interactions, and chance events. Patterns form, break, and reform in unpredictable ways, yet underlying structures, laws, norms, and natural limits guide the overall system. Creativity itself thrives at the boundary between chaos and order. Too much chaos leads to confusion and collapse. Too much order stifles innovation. The tension between these forces drives evolution, progress, and adaptation at all scales, from life itself to human civilization. In the natural world, we observe fractals and self-organizing systems that embody this balance. Trees branch in complex, yet predictable patterns. Rivers carve intricate networks through landscapes. Ecosystems maintain dynamic equilibria. These phenomena are neither completely ordered nor purely random. They are emergent, arising from the interaction of simple rules with chaotic variables. Nature demonstrates that complexity and stability are not opposites, but partners in the ongoing dance of reality. Cosmologically, order and chaos shape the ultimate fate of the universe. Gravity pulls matter into structures, creating galaxies, stars, and planets, while dark energy stretches space-time, driving expansion and separation. Collisions, explosions, and quantum fluctuations introduce unpredictability, ensuring that the cosmos evolves rather than stagnates. This delicate interplay allows for environments where life can emerge, thrive, and adapt. Without the tension between order and chaos, the universe would either collapse into monotony or dissolve into meaningless randomness. Philosophically, this dance invites reflection on meaning and purpose. Life, intelligence, and consciousness exist at the interface of order and chaos, emerging from the interaction of rules and chance. Our ability to reason, create, and imagine mirrors the cosmic pattern, structured thought born from unpredictable inspiration. The universe, in a sense, writes its story through this tension, weaving unpredictability into the fabric of stability, producing a narrative that is both coherent and endlessly surprising. Even human understanding mirrors this cosmic dance. Scientific theories provide frameworks of order, yet each discovery introduces new questions, revealing the chaotic depth of reality beyond. Our knowledge is provisional, structured yet subject to revision, reflecting the universe's pattern on a smaller scale. Curiosity drives us into the unknown, where chaos and unpredictability challenge our understanding, forcing adaptation, innovation, and growth. Ultimately, the dance of order and chaos is the engine of creation. It sustains the universe, enables complexity, and fosters the emergence of life and consciousness. To witness it is to see reality as a living, evolving system, neither fixed nor random, but balanced in perpetual motion. Every star, every particle, every heartbeat participates in this rhythm, a testament to the dynamic beauty of existence itself. It is at this intersection of predictability and unpredictability, structure and spontaneity, that the universe reveals its profound elegance and infinite possibility. As we gaze into the cosmos, trace the spirals of galaxies, or probe the quantum realm, we are confronted with an enduring truth. The universe is vast, mysterious, and infinitely intricate. Each discovery reveals both knowledge and deeper uncertainty, drawing us into an unending journey of inquiry. The final frontier is not merely space or time. It is understanding itself. To explore the universe is to participate in the infinite quest, a pursuit of knowledge, meaning, and connection that may never be complete, yet defines the very essence of human curiosity. From the first flickers of consciousness to the creation of telescopes, particle accelerators, and satellites, humanity has been driven by the desire to see beyond immediate perception. The night sky has always inspired wonder, but modern science has transformed that wonder into systematic exploration. We map the heavens, detect signals from the edge of the observable universe, and peer into black holes. Yet each revelation produces more questions than answers. What lies beyond the observable horizon? What is the nature of dark energy and dark matter? Are there other universes, other dimensions, or even other forms of consciousness? Each answer is a doorway, opening onto new mysteries. The infinite quest is not solely about outer space. It is equally an exploration of the inner universe, the quantum domain, the brain, the nature of consciousness, and the fundamental structure of matter and energy. Quantum mechanics challenges our intuitions, showing that reality is probabilistic, interconnected, and stranger than any imagination could fully capture. Neuroscience, psychology, and philosophy probe the inner landscapes of mind and awareness, asking questions about free will, perception, and the self. In both realms, we confront the boundaries of understanding, where the familiar dissolves and uncertainty becomes a horizon of possibility. Curiosity itself is the engine of this quest. It compels us to question, to experiment, to theorize, and to imagine. It drives innovation, discovery, and the creation of knowledge across generations. Human beings are unique in their capacity to reflect on their own existence, to probe the nature of reality, and to search for meaning in the cosmos. This relentless pursuit, though never fully resolvable, imbues life with significance. The infinite quest is a mirror of the universe, dynamic, ever-expanding, and rich with possibility. Science and philosophy converge in this pursuit, each offering complementary pathways. Science provides tools, models, and frameworks to decode patterns and uncover mechanisms. Philosophy provides context, asking why the universe exists, what it means to observe it, and how knowledge intersects with purpose. Together, they transform wonder into inquiry, awe into understanding, and mystery into meaningful exploration. The infinite quest is, therefore, not merely a scientific endeavor, but a human one, bridging logic, intuition, and imagination. Yet the quest is also a humbling confrontation with our limitations. The universe is vast beyond comprehension. Galaxies stretch billions of light years across. Black holes warp space-time beyond recognition, and quantum phenomena defy classical logic. Even the best instruments and the most sophisticated theories capture only a fraction of reality. Knowledge is provisional. Certainty is limited. But it is precisely this tension between the known and the unknown, between mastery and mystery, that propels the quest forward. Curiosity thrives in the face of uncertainty, and wonder deepens when answers are elusive. The emotional dimension of the infinite quest is profound. Awe, fear, inspiration, and humility intertwine as we contemplate the immensity of existence. Looking at the night sky or a quantum diagram, we feel both our smallness and our significance. Small because of the universe's scale, significant because of our capacity to observe, reason, and imagine. Our consciousness allows us to engage with reality, to trace patterns, to formulate questions, and to glimpse truths that would otherwise remain hidden. The journey is as much internal as external, a reflection of the cosmos within the mind. Collaboration and connection define the modern quest. Knowledge is cumulative, building across generations, cultures, and disciplines. Astronomers, physicists, biologists, philosophers, and thinkers of every kind contribute to a collective understanding, each insight adding a piece to the infinite puzzle. Technology accelerates this process, allowing us to probe deeper, measure more precisely, and communicate discoveries globally. The infinite quest is therefore not only personal but communal, a testament to humanity's shared desire to explore and understand. Even as the universe expands, so too does the scope of questions. The search for life beyond Earth, the origins of consciousness, the fundamental laws of reality, the nature of time and space, all remain open. Some mysteries may remain forever beyond reach, yet they inspire continuous effort, creativity, and reflection. The infinite quest is less about arriving at final answers and more about the act of seeking itself, the engagement with wonder, the pursuit of insight, and the confrontation with the unknown. Ultimately, the infinite quest defines both the universe and the human spirit. It is an endless journey through the vastness of space, the subtleties of quantum mechanics, and the depths of thought and perception. It embraces uncertainty as a source of discovery, complexity as a source of insight, and mystery as a source of inspiration. Through this quest, we participate in the unfolding story of existence, tracing the architecture of reality, exploring the boundaries of knowledge, and connecting with the cosmos in profound and transformative ways. The universe's secret architects may remain hidden, and the ultimate truths may elude us, but the infinite quest ensures that our journey of understanding continues. Each question, each observation, each moment of reflection brings us closer to grasping the delicate interplay of forces, laws, and patterns that shape reality. In the end, the pursuit itself is the answer, for to seek knowledge, to confront mystery, and to marvel at existence is to engage directly with the universe. The infinite quest is the expression of life, curiosity, and consciousness, a journey without end, a story without finality, a testament to the boundless wonder of reality.